I think golf is and this one was really nice. Too many bunkers, right? You had to climb into the bunkers. There's a couple on this one you have to climb into. On the 18th.
The 18th is a bit deceptive.
Are we online?
We are active, we are recording, and we're out to the broader population as well. So, good. All right, well, first of all, thank you very much for coming, Kishan. It's a great pleasure to have you here. So Kishan is a professor of physics at the University of St Andrews and an honorary adjunct professor at the Center for Optical Sciences at the University of Arizona. And he heads a large 20-plus group working in various aspects of photonics, including micro-manipulation and biophotonics. And he's published over 300 journal conference papers, with many in Nature and Science. And his group won the European Optics Prize in 2003, and he was elected to the position of Fellow of the Royal Society of Edinburgh in 2007, and Fellow of the Optical Society of America in 2008. And in 2008, he also received a Royal Society Wolfson Merit Award, and in 2009, he was made a Fellow of SPIE in the USA. And today, I'm very pleased Kishan's going to talk to us about new directions in optical sensing and manipulation. So over to you, Kishan.
Well, thank you, Bob, and I very much appreciate, Bob, the invitation. It's been a pleasure to meet you, Phil and Shetal, and to be here. I'm just someone who's passionate about light. I mean, actually, I'm a failed astronomer. I wanted actually to do an astronomy PhD actually here in Manchester, but I think I came up and then I realised it was 1 minute of stargazing and 3 months at a computer at that time, and I thought, that's not really what I envisaged, but that's sadly, like most people in this room, sadly, I'm chained to the computer as well, anyway, regardless of what I do. But I left, I actually worked in the city, but then I came back and I decided to follow more terrestrial pursuits in pursuit of my interest in light, and I'm actually a quantum physicist by training. But as you'll see, we are doing things right at the cutting edge of biophysics, and I firmly believe in interdisciplinarity. What I really want to do is, I've got my own agenda in photonics, and I can think of things that I can really push hard there. But I'm going to show you today are things where we've worked together with other colleagues right around the world to try and push light and to do what light can do. And what's incredible about light is this laser point and this beam is something we take as ubiquitous now. And the laser coming around in 1960, and of course, light features a lot. This year is actually the International Year of Light. Some of you may not know, it's from UNESCO, and there's lots of things going on if you look at the Institute of Physics, for example. But the main thing is I'm very surprised at what light can do. Let me give an example why light shouldn't do very well. Is if I hold my laser point up to my finger, it doesn't go through. So it's kind of hopeless. You know, and you look at that and you say, well, that's the end, because light's just going to do some surface things, and it's really not going to penetrate very far. But incredibly, it's supporting a revolution in healthcare, in fundamentals, and I'm going to just give you a flavour today of some topics that I think may pique your interest. So my group has broadened to an amazing number of things, but we'll start with that. So some of you will know where this is. This is where I St Andrews. This is the famous halogram where golf was supposedly invented, the RNA, that's the first. That's the 18th, that's the Swilcan Bridge, where all the famous people take a little stop as they finish their last round, and you may have seen Jack Nicklaus on there 5 years ago. So one of the majors is held in the UK every 5 years. It cycles round. This year it's St Andrews' turn again. So between the 16th and 19th of July, if you turn your television on, you'll probably see, hopefully, weather is at least as good, if not better than this, but we always hold with bated breath what the weather's actually going to do in this place. But it's a lovely spot. Where are we geographically, and where am I? So that's the course there, and that's physics. That's where I am, but I'm fortunate enough to have, they actually designed the medical building right next to me based on some of my work and some colleagues, and we've got a physical bridge. As a professor, you kind of, as you went up the ranks there, you kind of migrated around the building to get onto this site with a nice view. By the time I made it there, a big granite wall was awaiting me. But that's the price of progress, I guess. But as you can see, we're very close to the golf course, so you can literally pop over. And this is the beach, which I haven't shown you, but it's a beautiful long beach. And some of you might remember the movie Chariots of Fire that was actually filmed there, which was an Oscar winner in the 1980s. Anyway, it's a lovely spot. It's the third oldest English-speaking university, but St Andrews doesn't have engineering, so you can see that. though we have sciences and they're grouped here, what we do benefit tremendously, I do, from medicine and also chemistry, which is just labelled here. But we do not have engineering, and that's decoupled to Dundee. And so that's maybe something where my move from Imperial has made, I've not really engaged with so many engineers as I would have liked over the years, but I've certainly engaged with the biomedical and other people. So this is just to give you an idea. So I'm going to give you right to the heart of where light fits. So light kind of has been fitting around here. So this is the resolution. In other words, how much can I see on whatever I'm looking at? And how deep do I go? And if we're lucky, light can get to about 1 millimeter. And many of you use electron microscopy or and ultrasound, which I know will feature prominently. And light is somewhere in between, and it's kind of maybe not as good as what you might like to do. Now, what we also have with light is this limit of diffraction. What that really means is, if I take this laser pointer and I want to focus it to a tight spot, I can't focus it to an infinitely tight spot. That's basic optics, which is known as diffraction. And that's the limit here. And that applies, of course, to electron microscopy, etc. And ultrasound sits here. But what we'd really like to do is do something better. Now, I can't answer for the other two areas today, but one of the things that optics has done is try to push. And it's pushed in these directions. So optics, in the last 2 decades, has really tried to displace high-frequency ultrasound and super-resolution. A lot of electron microscopists are now using optical methods. And I can go into details afterwards if you like. And one of the examples of where you might want to do that is neuroscience. So this century, people might say it's the century of the light, it's the century of materials, or it's certainly the century of the brain. Whether we like it or not, we have massive challenges with healthcare and the brain, and people would like to understand the working of the brain. So what we'd really like to do is get to really good resolution, i.e. nanometers or better, but we'd like to go deep inside whatever we want to look at. That's pretty obvious. And so these are acronyms you may have heard of. But you might not have heard of these. These are two that are, one is called optical coherence tomography and one is light sheet. But light is pushing out the boundaries. It's displacing technologies in a way that's surprising many people, including myself, in a very pleasant way, having been part of that. So I'm going to give you a little flavor of some of these methods and also molecular resolution using Raman that may interest you. So where does resolution come from? The idea is you make this light spot, and if you put something like a delta function into a box in optics, you don't get a delta function out of spot, you get a pattern like this. This is known as the Airy disk pattern. And what happens is, if I have two objects close to each other, here you might tell me where the center of each of those is, but here it gets hard, and that's the resolution limit. How close I can get those two patterns, and it'll tell you where the centers are. Very simple optics. And if you go to Jena in Germany, where Zeiss have their center, you can see this on the street. It's a very busy road, but you see lots of random physicists and scientists stopping in the middle of the road. And this is Ernst Abbe, who did laws of diffraction and studied there in the late 1800s. And if you go there, you see there's the diffraction limit going down to about 200 nanometers, but there's his equation. And that equation was the one that was broken, which is why the Nobel Prize in Chemistry went to this field. Okay, so if you're ever in Jena, pop in and have a look at that. Very, very nice. So how do you break this limit? There are a lot of ways, and I won't have time to go through. I don't want to give a tutorial, but these methods are proving extremely beautiful and elegant. And if you want to have a look, just have a look at the Nobel Prize lectures in chemistry. So Stefan Hell, Eric Betzig, and Myrna won these methods. And for example, you can now see nanometric precision here. This is looking at vacancies. For example, nitrogen vacancies in diamond has now been resolved using this. It's not just biology that's benefited, it's structured illumination, and there's other time-varying methods, stochastic methods. So you kind of just sparsely illuminate things and let light come from one object and then another, because when I looked at that resolution, I was kind of looking at both things at the same time. So you can use temporal and spatial shaping to get around that. Let me just give you a quick example. This is data in our lab, and this is my quick way of explaining structured illumination. So if you go home and take a piece of nylon and fold it over, you get these beautiful patterns. Everybody's seen them. If you're on a train and you look past railings, you get this pitch. But look at that pitch. Let's say this is my sample and this one on the top is a frequency I know. I don't know the frequency below. I put one piece on top of another, but you can see, look at that pitch there. That I can record. If I can record that pitch and I know the pitch of the pattern that's rotating, I can work out from Fourier optics the pitch of the frequency below. It's as simple as that. And that's called structured illumination. So here we have chicken fibroblasts, and this is an example where, with colleagues in the Albert Einstein Institute of Medicine, they were using electron microscopy to actually look at renal biopsies, which is actually a big problem in the Bronx due to alcohol in their diet. They are now using our structured illumination microscope to look at that. We also have pictures of beautiful photonic crystal structures I can show you for the first time done under super resolution. I apologize, I didn't put that in this morning, but that's some example of where electron microscopy is being displayed. But let me now go to something that I think you will know a little bit more. Whoops. Is Raman. So Raman is, if you're not sure what it is just inelastic scattering of light. So C.V. Raman on a trip to the Mediterranean was entranced by the beautiful colours of the turquoise waters. We are at St Andrews, but they're a little bit colder there, so he probably went swimming, and enjoyed the water in more of a way than I could in Scotland. But he looked at those colours and went back and wondered what happens. And we know that every object in the world, materials or otherwise, scatters light, and it scatters it inelastically. So what happens is, light comes in, and it scatters off some virtual state. The bottom line is, I can shine this laser in my hand, and I will get a Raman signal right now. It shines off. And what happens is, the light coming off my hand is shifted slightly in energy. And that energy is a reflection of these vibrations. So this little cartoon that's a little bright here, but you can see those photons are coming off of different colours. And with all the molecules, I can just write down and get a fingerprint. And that fingerprint is, if you like, a signature of what I've got. So it allows me to diagnose what I have. And beautiful things exist. So Raman comes out here. I apologize due to the brightness of the screen. There's fluorescence, which comes out more slowly. There's other competing processes. But Raman is very, very weak, but it's very powerful. And it's at a tipping point, in fact. So I'll show you some things that we've done. We've removed Raman, the background from Raman. So one of the problems with this has been, as a bottleneck, is the background. So we've used a clever little dithering method that shifts the Raman feature along here, and then we take a derivative. Basically, what happens is, the background fluorescence doesn't shift. If you have one laser and you shift it just 1 nanometer, for example, the background fluorescence stays the same, except the Raman follows because that vibration gap has to stay the same. It's the vibration of your molecule. And then you use simple multivariate analysis, which says, what's the biggest moving feature in your scatter plot? Well, it's actually the one I've just done. It's the Raman. And it immediately extracts out what you can actually get here. If you do that, for example, here is just a cell. And normally you get these horrible big undulations, but instead we can actually get beautifully zeroed plots without any mathematics. It means you don't have to rely on somebody fitting a polynomial or depending on where they're doing the experiment. It absolutely works anywhere in the world. Why is that exciting? It's exciting for biology because in biology we want to look at sensitivity and specificity, false positives, false negatives. So you want to make that as accurate as possible. So principal component analysis is part of it. I'll just put this up in case people are not aware. This is one of the most amazing techniques in the world. I think it's vastly underrated. It projects data into like an eigenmode or eigenvalue problem and allows us to look at maximal variances and orders them. And this is actually at the heart of some of the most amazing things that I've seen, actually. And it's something I think everybody should try and get to grips with. Even the Carl Person came up with it in 1905. But it rotates data sets to look at biggest variances. And when you do that, you can do some beautiful things. What you can do is you can get an algorithm and you can train a system. You can get that Raman data or whatever it is, and it can cluster. This is the first, if you like, the first biggest variation, the second one, and cluster it. And what I really like is something on a diagonal. So this is what's called a confusion matrix, which I hope you're not already. What it means is, every time I say I've got a cup of coffee, do I really have a cup of coffee? So in other words, everything should be on the diagonal. And if you do that, you can use this. So you train it, you take your unknown data, and then you do that. Where is it used? You've all been to Heathrow. You go through and those little colours on those little bars that flash red and then they go green. I know that uses this kind of algorithm for face recognition. It's absolutely used everywhere. Let me give you another example. Those of you children might recognise this feat. Does anybody know who this is? This is Dash in the 2004 Pixar movie, The Incredibles. So how do Pixar make movies very, very quickly? They don't just have somebody drawing thousands and thousands of random faces and putting them together. I mean, if you think how hard it must be, they use eigenvalue bases to do that. So this is Dash's eigenbases, if you like, or principal components, used in this what's called a varimax rotation. And you can look that up in this paper here. And this is the basis of what I was telling these gentlemen last night about how to use minimal number of illuminations to get information out without redundancy. How do I know the shape of something or even the Raman signal? It applies everywhere. So it's really exciting and interesting, and I think is used more widely than you may appreciate. But in some areas, it's completely ignored. What can you do? More seriously, this is an example of, we've done several studies. So here with modulated and dithering and normal Raman, we can get increases in sensitivity and specificity over the standard feature very, very quickly. Another feature we can do is we can take Raman with the lights on. Many instruments that you use and I use, you have to turn the lights off. What if you could just take a probe and just take a Raman signal? It sounds impossible. You can now. And this is how you do it, because a clinician or anybody doing anything in the field doesn't want to do that. So here, what happens is, because we dither it, we know the frequency, and we can take room lights out. That's extremely important in a practical situation to do that. It's an extremely simple modulation method. So here's that confusion matrix. So this is for urine and bladder cancer, which turns out to be a very good application. You can see how hopefully most of the numbers are on that diagonal, proving that we can really classify cells placed in urine over certain time. So this is an example of something one might do. We've also combined this with other imaging modalities, so even putting modulated Raman into MR suites. So the surgeon, or somebody where you don't want metallic parts, we've designed completely all plastic composite probes that can go in and give you, with heat shrinkable sleeves, going in to allow the surgeon to see what they're doing and what they're guiding. This is work done with Ninewells Hospital in Dundee, which has been very exciting, and we've got a new grant to pursue this further. So again, taking out the metallic parts. One of the things that I think people know about is reducing the amount of volume you might use. So you might say, I've got, I don't know, a cup, and I've got a lot of liquid, for example, here, but do I really need all of this to know that I've got milk here? What I really might want is to just take a small fraction of this and not waste it, because I might want to use it for some process. And so the area of microfluidics has emerged as a very, very powerful idea. So here's an example, and this is an ultra incredibly, this actually has no lenses. It's 2 pieces of plastic and 2 fibers. This is a very clever little geometry that we designed, and using the modulation, this is urea detection on the same chip. So basically, it turns out these fibers cost $10, and you can actually excite at one wavelength and collect orthogonally. You don't even need lenses, which is very interesting. And we can do this online and a few other things. But anyway, the bottom line here is this is for urea detection. But then one evening, after a rather arduous and not the most pleasant dinner, but it was interesting. I had my board for one of my grants coming in, and they were talking about impact, which is a word that strikes fear in the heart of academics over the last decade and beyond. And when I was walking home, I was walking past one of our very nice off licenses and looking at whiskey in the window. And it occurred to me, I thought, I wonder if anybody's ever taken a Raman spectra of whiskey. So I started reading. And it turns out whiskey is a £7 billion industry. Counterfeit whiskey is worth $2 billion. I actually have colleagues in Hong Kong and everywhere. People buy expensive whiskey. You can buy bottles on eBay. People put fake labels on. If you go to Heathrow, you can easily spend £100 on a nice bottle of whiskey, and many people do. But it turns out a lot of the manufacturers are worried about counterfeiting and what people put into whiskey and additives. And it turns out nobody had done Raman on whiskey at all. So here's some interesting things, and here's well, even the British Medical Journal said a little whiskey is actually good for you. Well, this is not. I'm not here to debate the health benefits of whiskey. I'm just here to tell you. I want you to be sure that what you're drinking is really what you want to be drinking. And there's also things like people spiking drinks or adding additives. So you may know about the Czech Republic, where there was a Slivovica, which is a plum brandy, which about 100 miners died, and the Czech government had to remove all alcohol from shelves for a couple of weeks. I mean, the cost of that to that industry was huge. In India, people die also of alcohol with methanol added and so on. So this was something that encouraged us. So it turned out something that was a small summer project and allowed me to buy spirits on a research grant has turned into something rather large, which is really a very 4 newspapers are brave. But anyway, here we go. WCRS is our wavelength chip. we have our little chip. It's exactly the same chip we did biomedical. We put a drop on, and there's the spectra of whiskey. These are these PCA plots, those rotating plots, and you can see, look at that, they cluster beautifully. Take the spectra. We don't even have to use, in fact, the modulation if we don't want to, and we can take Raman and fluorescence. And it turns out fluorescence also is a fantastic marker because people put congeners. If you go to Scotland, they give you the beautiful romantic story of the stream flowing down and the soil and everything. And you have to put it all together to make that very special drink that you're about to taste at the end of your tour. It is very special, and it's actually individual. And we can actually distinguish all of these whiskies very well. We can do more. The Raman can tell us to 0.1% accuracy the alcohol content. You can't sell Scottish whiskey unless it's 40%. Okay, so there's criteria for selling this and standardizing it. This is our chip again that we worked on. And here you can see all these very famous brands. Maybe your favourites up there, if not. Don't worry. And you can see how we can actually do that. This was just in a lab, so if somebody pushed this harder, we could do even better. And then we made it compact. And here's something I really would like to point out to you. You can actually tell the difference between the age of the whiskey. And for the real connoisseur, you can actually put a whiskey in a special cask. So, for example, in a port cask or a sherry cask for the last 1 or 2 years of maturation. Again, it picks it out beautifully. And we've made this into a compact design, 0.5 meter or so. But then we thought that's still not good enough. But anyway, this one we took.
Okay, Grant.
Now
you take a sample of it, but you can spit it out. I think there's a spitting spittoon somewhere.
I'm not going to spit it. We're nearly at the end of the show. It's going to be fun.
So Dara, you can taste that and see if you know what type of whiskey it is. And over here, the computer is going to have a look at this sample I've taken.
It's a nice whiskey. Glenmorangie, actually. Yeah. Right, so we run the light through it.
Now the computer comparing it and says it's a pure malt, correct, but a Japanese
pure malt. Okay, so let's find out if the computer is right, if I'm right. Is the computer right? Yes, it is. Very good. Well done. Congratulations. Fabulous.
So that was something. Now that was actually a very stressful day for me. Because if you've been to a BBC TV studio, you can see blaring lights, people stomping up and down, fantastic temperature. This is not a beautiful research lab at St Andrews on an optical table. And we had to train that guy in 15 minutes to do that. And it taught me a lot about taking something out of the lab and making it robust. But we were very lucky, we got away with it on live TV, and it was fine. And Dara O'Brien, as many of you know, is an astrophysicist and is a great supporter of science, full stop in the UK, a great ambassador. But we went back and then we pushed even harder and we came up with this. So this is a brand new device that we're with a company. This is a Raman spectrometer that's the size of a Walkman. And this is real-time testing of whiskey in a vial. So you may even want to only use a microliter, but you may get away with a few milliliters. You put it down. This is all real-time. So these are just 6 whiskies we've trained for. So what you do is train. You get a database. You put this in your pocket, and you go out to the field, and you just click. Put it in. It's really... The biggest problem with this, believe it or not, was the variability of the vial. The glass in the vial could have impurities that we couldn't control. But that's, I guess, probably readily solved. But it shows you we can just click a button and get an answer. So this is the kind of thing that I think could be very exciting for portable Raman. And it could be used for many, many other liquids as well, in fact. There we go, there's the data, and it tells you which one, and it pops up. So if we train this, it's actually coming to London next month through the company M Squared. It helps us bring this to market, hopefully, if you're interested in a demo. But we've done even more. Recently, we've just done the same thing for olive oil. Did you know the olive oil you have sitting in your kitchen, there's actually very good ways to store it. Now, we're all interested in the Mediterranean diet, but if you actually expose olive oil to light, the temperature variation in your kitchen can actually make a difference to the fatty acid content and what you actually have. And it turns out we can characterize extra virgin olive oil, which is actually a big problem and a big issue for the Australian government. This is a big report they did 2 years ago, and for Greece and many other countries in southern Europe. So this is an example of what one can do. But your imagination is just limited by what you can actually put in that device and characterize. And we've got some more innovations to put in different inserts into that. But that just gives you an idea of where that could go. Again, all done just by reading. So microfluidics has interested me a lot. So let me just go back to... but, you know, one of the things is I always wonder when the field doesn't really take it to the next level. So we can read hundreds of papers in great journals about chips, but chips get clogged. Biofouling. So there's this area that some of you may or may not know, which is called paper microfluidics. I don't know if anybody's heard of that. So instead of actually using a chip, why don't we just squirt something on a little piece of paper and use wax channels to stop the liquid dispersing out, create hydrophilic, hydrophobic chambers. So this is what we've been doing. This is so simple, it's a postage stamp. And then what we do is a 3D printer, we can heat and put little wax channels. It can be any pattern you design. And then what you do is, as you've seen in real time, you spot it. Capillary reaction just takes the liquid up, and here we're doing an enzymatic reaction for glucose. And for a protein, BSA, and this is a control sequence. You see the color change, and you record that. We actually have this hooked up to an iPhone to be disposable right now. One thing we've just recently done, which is impressed, is actually for the first time to characterize drugs on this piece of paper. And you throw it away. It costs nothing. Absolutely nothing. And you can design anything you like. Of course, you won't get the accuracy and sensitivity because you don't have extremely well-defined channels. But if you're doing a very fast test, this is extremely powerful. And here, for the first time, using the modulated Raman I just showed you, we're able to distinguish the Raman signal from the paper from what we put on. And one of the problems a local hospital has is people's drug intake. So can you take a blood sample or something from fluid and actually measure the drug content? We can measure now nanomolar on pieces of paper and throw it away. So we think this is very exciting, and we've actually got a thing called lab in a tube. We have a little piece of paper, you put it in, and we've got a light source, a piece of paper, and one of these beautiful little Sony Wi-Fi cameras. I don't know if you've seen them. They're Wi-Fi hotspots, $200. You put a camera in, it takes a beautiful picture, and you can sit there with your iPad and just slot things in and out. Absolutely beautiful. We call it like lab in a tube. I can show you that maybe later on. So let me show you a little bit more about some in-depth imaging now. So one of the things that's coming up is we've seen a little bit about super resolution, and when you do any Raman, confocal, multiphoton, whatever it is in optic, you focus a light beam down through a microscope, you put your sample in. And this is not our work, this is work in the US of somebody looking at mouse vasculature, and this is a green dye flowing in a mouse vein. But what happens is when you focus light down, you might get your excitation volume here, where you get the signal from, but of course you can see there's light everywhere, isn't there? There's light all along that code. It turns out that for certain materials, and certainly in biomedicine, the less light you can use, the better, because we would like to use only light where we need to get a signal from. What I'd ideally like to do is just have light here, but not above and below. Now there's also multiphoton, which means you use 2 photons. So in the world of optics, 2 red photons is the same energy as a blue photon. So I can use 2 of those and get a multiphoton process. You can see I still have to illuminate above and below with some red photons. So one of the biggest revolutions that's coming along, which is verging on displacing this, is called light sheet microscopy. I now turn my attention away from... Right. And what is light sheet microscopy? It's exactly what it says on the tin. Instead of having a point, imagine I had a light beam that was the shape of a piece of paper, and I could optically slice things. And then all I do is I look orthogonally. Now, why would that be interesting? Well, here, I put a sheet through that board, but either side of that sheet, I have no light. So I'm not illuminating. In contrast to the previous picture, I'm not illuminating above and below the region that I'm excited. I'm really making beautiful use of my photon budget and any damage. This actually goes back to this beautiful history paper here in 1912. Zygmundi won the Nobel Prize in Chemistry in 1925 for looking at cranberry grass, red particles. Beautiful geometry, but it's very, very simple. Let me just show you the kinds of things this can do. This is before Obama announced the £100 million brain initiative. This is calcium signaling in a whole zebrafish brain. Again, done. So now you get wide field, super cheap imaging over large volumes. That's a beating heart imaged in real time. And this is some work from Eric Betzig published in Science in December. So he's a Genelia farm, won a third of the Nobel Prize last year. Let me show you what we've done at St Andrews. This is one of the big problems in optics. If I want a sheet of light, if I ask you to make a laser beam in the shape of a piece of paper, you think that's silly. Because I can focus light down, but we all know it diverges. And that's standard optics. It's known as the Rayleigh range. So the depth of focus, the tighter I focus light, the quicker it diverges either side of that. What I'd really like is a beam that was that narrow, that I could really slice, but went along over a large field of view. Sounds like magic. It can be done. And so we've done that. I won't go into the detail, but we use a light beam that's named after Sir George Airy, the British astronomer, called the Airy beam. It's actually used in quantum physics, believe it or not, but it has magical properties in terms of its frequency reconstruction, and it can be made with a single piece of glass. It's a very strange beam that's asymmetric, and the asymmetry means that when you go into what we call the modulation transfer function, which means how do I recover frequencies in my object? Remember, I was talking about that in the pieces of nylon. So I'm not wearing a stripy shirt today, but if I was wearing a stripy shirt, it might be easy for people at the front of this room to see it, but at the back, because they have a smaller cone angle or numerical aperture, they might not be able to see the pitch of it. Okay? And this is what tells you how much information comes through that black stop. And here you can see, because of this asymmetry, that never goes to zero. What does it mean? It means something very special. It means you can take beautiful pictures like this. Now, this is something I think we are starting to look at materials with this. These are actual images at St Andrews. This is cancer cells, and you can see the resolution advance when we get. This beam is trivial to make. This is a little animal that lives in St Andrews, and one of the big problems is what's the spatial periodicity of its muscle on its tail? Well, I hope you agree. A little bit easier to see that on this one than this one. And this is, again, this little detail here. But you can see that all by shaping the light. So incredibly, we can shape the light with a little piece of glass and actually create, essentially, a large field image just like that. We can do more. So this is exactly the zebrafish you saw before, but now taken over a factor of 2 in information. So this is poised to displace confocal multiphoton, and we are inundated with people who would like us to build one of these for them, for a lot of reasons. This is from David Lyons, who supplied the zebrafish. Apologise, it's saturated on the screen there, but the images, all our biomedical people have just stood back, and we are swamped with people wanting to use this. So, what I like to do now, I'm sorry, it was just one thing that was there. I didn't actually, for some reason, did that not come out? I didn't point out this. This is the device. So I don't want you to go away from this room and think, oh, well, Kishan's got this big labs. It's an A4 sheet of paper. So we've made the whole thing compact. My philosophy is to take instruments that you think you have to go to St Andrews for and bring them to you. So we've taken this to Oxford, where they've resolved something for brain slices, and we've had a master's student in chemistry use it from scratch. She's got a fantastic project already, and we're publishing a paper on that. So this is where I think microscopy can really go. So you can have these instruments do that. Let me now just, if I may, just for 10 minutes, just go back to Raman and tell you about OCT. So Raman gives me the molecular information, and we've seen that could be good for biomedical, it could be good for fiber probes, and it might be good for whiskey, olive oil, and any other liquid you might dare to put into that little Walkman-sized device. But molecular information isn't enough. So today, just like you might go to a doctor, or you might want multiple bits of information to confirm a result you might have. That's very sensible. And in the world of photonics, we call that multimodality. So one of the other things that's been very exciting is known as optical coherence tomography, which some of you... Optical coherence tomography is a £5 to £10 billion market. In fact, everybody in this room will probably have an OCT scan in their lifetime. What is OCT? It's very simple. Instead of molecular information, I'd like to get some morphological information. What does that mean? If I shine light at this, let's say I've stacked some different pieces of glass, I shine light down, you will not be too surprised if at every boundary a little bit of the light is reflected back. So in the world of optics, we would say there's a slight refractive index difference. There's a mismatch. And so some of the light's transmitted, some's reflected. Absolutely trivial. The question is, how do I record that? What I'd like to do is record each of these boundaries very, very accurately. How do I do that? Well, very simply, what I do is you might say, well, all of that light's coming back, so how do I distinguish that beam from that beam from that beam? That's really what I'd like to do. So we use a beautiful concept of interference of light. And what we say is that, if you look on this diagram on the right, which is a fiber, so here's my sample, but what I do is I move this mirror. And what I do is I use a light source that in the world of optics is bad, in what we call coherence. In other words, it's only when the path length from that arm with the mirror matches that distance to, say, that layer, that I get an interference pattern. Otherwise, the interference is moving around and it's washed out. And so as I move that mirror, what I'm really doing is I'm optically slicing in here. And that's how doctors are going to take pictures of your retina and look for glaucoma, macular degenerate disease, and so on. We've done a number of innovations here, so here's our idea. You have a delay line, you move it, and you can take pictures. So the coherence is low, so I wouldn't use a laser. In fact, it's just a little LED. And in fact, we have devices that we've taken around the world for this that are very, very small now. And the beauty is, you only have the interference when this path matches the path to that point. So I distinguish between different layers. Why would I be interested in that? Well, I can add two things together. I can take chemical information and morphology and combine different formats. This is all very nice for that, and we can do beautiful things. This is data from our lab combining, this is renal biopsy, taken at the Bronx at the Albert Einstein with these pathologists here. We ran over 5,000 samples, and that's what a doctor wants to see. So if you have a renal disease, you can look at glomeruli, which actually filters your blood to urine. You see those black holes. That's actually without the doctor even slicing it. No damage whatsoever. Just done with a light source in this device, and it's just there. That's it here. Taken there with a pathologist. So it's absolutely portable. Could be made smaller, as you'll see in a second, but you can see how exciting that might be. All right, that's fine. That's not my... That's not,
Don't do that.
don't do that. Always later. So let me show you where this is going. This is not our work, this is a group in Romania who for the first time have looked at, I guess we've mentioned fractures. Now please forgive me because I'm not an expert in materials. This is the first time OCT has just been used to look at ductile, brittle, fatigue materials and actually compete with an SEM. So I'm now talking about a device. This is actually a handheld OCT. There's very many of them. They are very rarely used in material science. So this is used, and this is a steel alloy called OL37 and OL52. Anti-friction alloy, and they've actually looked at, because I think with ductile fractures are better than brittle ones because they have this elongation, it's a little bit easier. They can actually analyze this with OCT rather than SEM. I think this is extremely exciting. We're currently starting some studies, and I think this would be a very interesting area we have to do. You can have this on a portable device, and it'd be wonderful to see how that competes. Anyway, this is this group here, and that was published just at the end of last year. So this is the kind of thing that OCT might be able to do. And it actually correlates beautifully. They've done a correlation between an SEM picture and an OCT picture. Now I think OCT could be a very exciting technology that could go and be used. It also might be used for looking at corrosion, because of course corrosion layers might have different refractive indices and material properties, and so again the very same principle I've just described could be done with a handheld device. I don't know. It's very interesting and worthwhile to think about. What more can we do? If I may just have 5 more minutes. So one of the things that I've been interested in is, I've been interested in thinking about how we can apply photonics for global warming. So we have a sea mammal research unit at St Andrews, and it's, if you have time, have a look at it. Its initials are SMRU, and I had to chat with them. They were looking at water salinity, water properties, and what they used to do, they had these little units from mobile phones, and they stuck them onto seals' heads with iodide, had a little nozzle, and the water would flow, and the seal would be swimming around. Of course, animals go in places we can't. And they do it naturally, and they do it at their leisure, and they come back. And the beauty was they swim everywhere. This device collects information, the seal pops up, transmits the information, and you've got yourself a data set. Beautiful idea. Made the seal apparently slightly unattractive to the females for a while, but apparently with natural growth and slight hair on their head, it fell off after a certain period. So they were back in the game after 6 months. But anyway, this was a wonderful idea, I thought. It's a beautiful idea, and they did a project with Motorola. But then fortuitously, Tom Brown and myself, we met some people on the Australian Antarctic division. I don't want to go into how we met them. But this was actually the paper of the week in OCT, in fact. So everybody's super excited about this, and Tom's giving an invited talk at the moment. I've been to Tasmania earlier this year, which is krill. So krill is something you might buy a tablet for arthritis. But krill also have changes due to ocean acidification. So their shell thickness changes. And so how do you monitor that? So it turns out using OCT, we'd like to look at their development as a function of ocean acidification. We can do this, and so that's exactly what we did. This is absolutely data taken in our lab for the first time looking at this. And in fact, the device is so robust, we were on a short list to go to the Antarctic on a boat, but there are obviously far more important things, putting photonics down there. But look at that picture there. And you can see that's just taken here. A very simple, compact apparatus that would fit here. There's obviously room for improvement. You can see the quality of that picture, and we can measure the shell thickness and now we can do it in live krill as well, with perfusion, and so that's beautiful. We don't have to damage the animal at all optically done here, using that very same principle that I've just described to you. And I won't dwell too much, but you can see on mine, but apologies for the contrast, you can see the heart beating, you can see things. What I want to get across to you, though, is you can do real-time in situ samples, put them in there, and get shell thicknesses out, and actually calibrate the instrument, and you can get a number on in situ, which is brilliant, and then you can throw that away. Here's another picture showing the heart and the stomach, and it's correlated beautifully to other images that they've taken. And we've actually measured, apologies, that's microns, the shell thickness here in this very first study, and it correlates beautifully. So they can now correlate that to ocean acidification. So I think I'm going to stop there, give it hopefully a little time for questions. Obviously I've done none of this work, but I hope I've given you a span of some of the excitement and how thinking in optics is going. I'm giving you a flavour, I hope today, of some of the exciting work that could be done, and there's potentially more. There's people on this board who've done really a lot of the work. Frank's a neuroscientist who worked with me for OCT, particularly Tom, Nicol and Joseph. Ravina and Bhavishan, I don't have a photo from Raman. These guys here did the light sheet in this corner here, particularly Tom Vettenberg and Johnny over there. I'd like to stop and thank you for your kind attention.
All right, so Kishan, that was absolutely fascinating. Thank you so much for that. So I just wondered if there are any particular questions.
One question. Regarding the light sheet technology,
Yeah.
About 3 weeks ago, Zeiss, they put on the market a confocal microscope with a light sheet technology that can do 3D light microtomography for, I would say, biological tissues. Have you been working with them on this technology or not?
Okay, I can tell you, okay, so we're working with a company M Squared in Glasgow to commercialize this. I've had several people who've looked at the Zeiss light sheet and they've looked at our one, which costs less than 1/10 of the price, and said the pictures are just as good. But I haven't done a direct side-by-side comparison, but Zeiss have a different philosophy. My philosophy is to make a light sheet I could put on this chair, bring here, in the back of my car. And that's what was done. Okay, but you're right, Zeiss are innovating in that area, but we have patents on this light sheet for extended distances with the beam shaping that we're doing. And there's lots more I can't show you today. We're a little bit even further ahead on that. But that's a very good point, yes. But what's good is Zeiss are pushing. And in fact, everywhere I go, everybody would like a light sheet microscope to see. They seem to be incredibly powerful. And maybe not in materials, but for the bio, phototoxicity is something you cannot ignore. You just want to use the minimum photon budget to get the answer you want.
In this university, there is a spin microscope.
Is that?
Microscope already.
Is that right?
Yes, I mean, it was brought to PSI 3 years ago. We reviewed it, in fact, and we had images of little black and white animals
Oh, yes.
moving the light sheet.
All right.
There are issues that are quite big and complicated, to be honest.
Oh, is that right? Yeah, so that's actually what we found. So, for example, with Nigel Emptage at Oxford, who does neurons and he's doing synapse formation, he wanted something in his lab. And you know what I think that's exciting about that is because I can't have a materials lab or a Home Office approved lab at St Andrews. You might have the right lab with all the conditions and samples. I need to bring it to you. That's what I like to do. Bring the microscope to you so you can do it here and then give me some feedback.
Sorry,
Yeah.
last question. Is it possible to borrow one of your, I would say, light sheet stuff?
Well, yes, because that's right. I didn't bring one down on the train with me, but yeah, we actually now have four. We have four light sheet microscopes at St Andrews. We have one large one, and we have three compact ones. One of them's at Oxford. One of them is we're making a brand new multi-photon light sheet with a new modality, which is going to be really exciting. And we have another one. But if you wanted to, we could talk about bringing one down here for a study. Absolutely, 100%.
Also in OCT, there are people here interested in OCT.
Sure, I'm sure.
Actually
that.
worked on a project developing OCT
Yeah.
imaging.
Yeah.
I'd like to ask you, what kind of frequency for your mirrors do you use, and how deep is the...
Brilliant. Okay, so you're right. There are a lot of people working in all these areas, but I think one of the things that people don't perhaps do, what we've done is innovated it to be small, compact, and portable. Maybe I do apologise because I didn't, because of time, I didn't explain. Let me give you an example here. We have a delay line, and you move a mirror, and as the mirror moves, you sort of take slices in your sample. That's fine, but nobody uses that. That's in the time domain. So now what we do is we switch to the frequency domain, and what you use is you use a broadband light source and illuminate all the colours at the same time. And what you use is a grating that disperses it on a camera. So each slice is going on at a different time. Let me give you a picture of how that looks. I've got an instrument picture somewhere. Did I have it somewhere? Yes, here. There's no moving parts. That's the beauty of it. Here, this was taken to Tasmania and worked straight out of the box. Okay, and we could obviously engineer it much more robustly if the need arises. So that's it there. So you see this? So we actually disperse the light with a diffraction grating onto the CCD. So it's no moving parts at all.
Some systems use analog inputs with an ADC.
All right.
So there's no system, there's no grating.
No, there's no grating.
But it's more complicated because
Yeah.
very high speed.
Well, my philosophy is at the moment we'd rather find the right problem, do a first study, and then optimize it for the problem that you might have. Because even in OCT, you can pick the grating, you can pick the wavelength, you can pick the NA of the optics. But rather than over-engineer it to begin with, what we've decided to do is have something that's stock running at 800 or so, and take images. And then if you say, actually, Kishan, we'd really like to get this resolution for this material or this biosample, then we can engineer it to what you might want to do.
And on the fracture
Oh, yes.
slide, what was the resolution of the test?
It's only microns.
It's micron.
Now that can be improved. I must please again stress this is not my work. I've put the reference for you, but it's something we've been thinking of as well. But I can give you the reference. I'll put the reference up here for you. But it's 10 microns or so. But it does start to show these features here, which I think is very exciting, and they've correlated it to an SEM, which is very encouraging for us as well. I would love to get some samples if you had some that we could
corrosion and oxide samples.
Exactly. I think that would be very exciting to do, and we are developing some compact handheld devices. You may be able to have a device that could just.
So if you had layers of, let's say, carbonate, iron carbonate scales, different layers, could you go through each of the layers with this technique?
You could. So, now you hear a very interesting thing, and I have slides on this, but I didn't talk about this. One of the big problems is, you see this problem? We can now engineer the light to go to the other side of my finger through beam shaping. So your question about how many layers we might get through, we're currently working on a very clever way to actually allow the light shaping to penetrate deeper. So we've got about a factor of 2 or 3. This is completely original to St Andrews, but whether it works will depend on the material properties and the transmission, and we may have to play with wavelength. But I think it will be very exciting to try. OCT, as I think I mentioned last night, was used for looking at fake paintings. So I think if you're looking at a deeper, so it should work. but it would be wonderful to try. I think it's an untapped area for the OCT market, and there may be other optics tricks we could try as well.
Last question.
Sure.
You showed the slide where you have a cell, and
Yes.
I'm interested in the engineering general.
Sure, that's fine, yeah.
Showing
The cell.
an acquisition time of 200 seconds.
Oh, yeah,
And I mean, many bioprocesses would have finished in that kind of time.
that is correct. This one, was it?
Yeah, somewhere, yeah, acquisition time.
It's 200 milliseconds, sorry.
Ah,
I apologize if it wasn't clear, it's the little m. So it's Raman
it's
isn't.
the top one, standard rank.
Yeah.
Oh, that's an error. Oh, yeah, standard Raman, yes. Yes, people take, standard Raman takes usually a very long time, which is why a lot of people have abandoned it or don't use it in certain situations. They use things like SERS, surface enhanced Raman,
Yes. Yeah.
which has its own problems because of reproducibility and the other things that you might need a substrate as well.
I mean, the systems that could do very fast run like that would be quite expensive.
Yeah.
And is there an interest in developing faster methods for that?
Or just Raman.
Yes, for SERS and stimulated Raman, for instance.
There
Like
is.
the work of Sheep in the
So Saniji at Harvard uses something called stimulated Raman
Yes.
for cars,
Yes.
carrying anti-Stokes Raman.
Yeah.
Absolutely right. These are non-linear processes. I can go into details of that. One of the problems with that is typically you have to tune to one or more bands.
Yes.
So people tune to typically the lipid band at something like 2850 cm or something, and you have to. It's quite arduous.
Multiple frequency system with an 8 off.
But the laser systems are horrendous, and they seem to still fill a lot of an optical table. But they are. But this is extremely compact.
What I'm trying to say is, if there's a push to get that to very fast speed,
Yeah.
actually it looked, there was a proposal made from here.
All right.
Actually look at, because the lasers are not 80 megahertz. And
Right.
the idea was to capture every pulse output
Oh, I
80
see.
megahertz. And that gives you quasi TV
That could be
rate
it.
speeds where you can
All
actually
right.
capture processes potentially.
Right, so we're not.
It's quite expensive.
It is expensive. So I don't. I mean, we don't. We do have a lot of nice toys, but I've decided to keep this side of the group as to the lowest and easiest level possible. You're absolutely right. There are other competing methods, but there's still a gulf of 2 orders of magnitude in cost and apparatus. This is just meant to be. I didn't talk about this, but the modulation also reduces the acquisition time by a factor of between 3 and 10, depending on the sample, which is modest but still extremely useful, we think. Because it removes the background. So if you took your SNR ratio, we get SNR improvements at that level. I can show you because it gives us a beautiful zero background.
More generally, it looks like the resolution for microscopy is a key issue. The people pursuing the highest resolution looks like last year, Nobel Prize gives a study can reach maybe 10 nanometer resolution. Would you like to comment something?
Sure.
Possible plan for the maybe
For the future.
if we can get 1 nanometer for optical.
Yeah, sure. So our renal biopsy slides, they were doing that with electron microscopy, and it took a day, and they did that, and we get 100 nanometers regularly in the lab. That's using just this nylon idea, the structured illumination pattern. If you STED microscopy, which uses a quenching beam that's annular, so it quenches the outside of the fluorophore, and then you just collect through the center of the vortex, which is what Stefan Hell did, you can get down to 15, 20 nanometers or so quite regularly, it seems, which is great. So I think what we'll see in the next 5 years is a lot of electron microscopy displaced with optics. It's just cheaper. But what I would like to do is take some of that and make it a microscope you can bring to you. Because everybody at the moment in all the universities is thinking of an imaging suite with a technician, but just like Lightsheet, we are developing a super resolution microscope that sits there. So yes, it will get very small, but also there are issues with, if you're doing biology, phototoxicity as well. A lot of the engineering has to go in the fluorophore because you need to reuse it. So a lot of people are engineering the fluorophore as well. And I think there's still a debate about how good a resolution you can get. But I have to say, Eric Betzig, last year's Nobel Prize winner, he pans his own method of palm microscopy, and he says light sheet and SIM microscopy are the best, interestingly. But that's a debate that's more detailed. But let me be assured, optics is here to stay at that level, and I think it's going to become a mainstay in many labs in the next 5 to 10 years.
Kishan, thank you so much for that really fantastic thought-provoking talk. And you can see from the questions already people start to make their own connections.
No,
So
thank you. It's
so
been very
Kishan's
interesting.
going to be around, so if you want to come have a chat with him afterwards, please feel free. Bill.
No, I was just going to say, if possible, it'd be great if you maybe have a trip over to PSI and there's some interesting discussions, because that's really where the centre of gravity is for this kind of work.
Yes. What, try and do that today, you think?
Well, I think Nancy might be able to do
Yeah.
that if you're
Okay.
if that's okay with you.
Yeah.
I have to rush, but
Yeah. I'm conscious some people have to go, but anyway, Kishan, thank you very much.
No,
Those
thank
who
you.
want to stay and ask questions, please do. Thank you.
Yeah, thank you.
Perfect. So that's very good. I think you can see from there.
Yeah, no, it's great. It was very nice to get some feedback. Yeah.
as I said, really the centre of all work in this sort of area is in PSI. Although I advertised it, it's obviously, it's the other side of the campus. So,
That's right.
but, that people don't necessarily think of it. But Med is one of the guys who is involved with the PSI, and I wondered if it's possible for you to have maybe half an hour to have a look at what they're doing. But also, I think I don't think you have time to see the X-ray. But one of the interesting things I'd like to think about are other ways of either the things fitting together, or can some of the same tricks be played with X-ray photons instead of optical photons, and can we do some of the tricks? So unfortunately I stacked up my meetings today, so I just don't have a chance.
We test a petrol station.
Maybe if you could send me an email at some stage, we can look at some of the other things.
I'll be delighted
And
to.
certainly the materials. I've been aware of OCT, but we don't have it.
Well, if you
our
had
lab.
some sample materials you wanted us to take some scans of, I'd be
I
delighted
think
to.
coating, certainly oxide coatings or scale coatings would be really interesting.
We'll be delighted to try that. And, yeah, sorry. Thank you.
So,
Yeah, that's fine.
is that okay?
That's
I
absolutely
think
fine.
that's really the best way
Yeah.
to really start to get these ideas.
Yeah, absolutely.
Because the PSI is where it's all happening here.
Okay.
We have a photographer around PSI.
Oh, okay.
It's going to start about 12 o'clock.
So go with well,
Right, let's go on.
Chantal and I'll come with you. We'll
I'm
go
sorry I
to the
missed you,
PSI.
Ryan.
These guys are the real experts. And have a discussion. Is that okay? Yeah. And then we'll just.
Do you want to very quickly grab a little coffee? Just
Of
before-
course,
This
yeah.
is all-
Please do. Please do.
You guys want a coffee?
I've had one.
It's getting too much now.
Balance my inputs and outputs. Right.
It's one of the things, Kishan, which is really, really interesting, because I saw you, basically it doesn't matter what you have on your stage, it's whatever fluids or whatever. If you could get the resolution down, I'm wondering if you could actually look at something like a corrosion process in real time.
Well, if you let me know what. The thing is, that I just don't know where to begin to model that or have a. If you had a sample, we could be delighted. Yeah, we'd be delighted to try something
That
out.
would be really
Because we were quite rare. We've got all the technology in one place at St Andrews.
Yeah,
All this imaging.
we can see things once they've happened, right? And
Yeah.
some of the.
So you want to get the time scale of these
So what
things.
you want to see is, you've got a piece of metal or something. You can see the corrosion starting. You can start to see how the pit forms
All right.
and things like that. That would be really interesting if you could look at that.
Do you know what time frame that occurs on?
I want to give you the idea if that's possible.
I mean, can you
speed it up.
You can speed it up. So could you if you did sort of time lapse imaging over a day or a week or something,
Yeah, you could do
see
that.
some features
Yeah.
appearing. That would be very exciting for us to try. I don't think anybody's ever done that optically.
I think that would be quite interesting. Very interesting. Because I'm trying to get that information, how these things start off.
Well, no, it'd be wonderful to hear what because we've got these things. I'm just tailoring it to the problems I currently have, and we've done a little bit. But it'd be wonderful to hear more on the material side of it.
But you can't detect water, can you?
Yes, you can.
You can.
So that's, I don't know if I mentioned this last night, I was at Rysvik at Shell and they wanted to look at water in cracks in rocks, in porous rocks.
Oh, that's right, you did. So you can.
Yeah.
Okay.
But
I always thought
we
you
haven't
couldn't,
had a
because
push to that, but if there was interest to...
Well, I'm thinking more water in fuels, in contamination.
Because actually on the phone I mentioned to him, the handheld Raman device, I said, you know, like the RON rating. I said, does anybody worry if you've got BP Ultimate or BP Normal or Formula One fuels? How do they test that?
Well, the biggest problem is water in aviation.
You mentioned that.
See that? So
If you were able to send us some samples, or we could come down here with something, then we could actually try it on our little vial system, if you like.
Or water in lubricants and things
Yeah.
like that.
So what you're talking about is actually we developed a system based on some frequency generation.
Oh, really?
To examine
Yes,
surfaces. And this gentleman is putting the optics on the table at the moment.
Okay.
It's in nowhere near where you make small systems, by the way. You but this is like a
Yeah, no.
system.
Everybody has to be able to read some. We've got big
They
systems
will
too.
look at, you know, like fuels and surfaces with water and so on.
No, I mean, this is still talking about the bulk fuel. So you remember that famous case about 6 years ago, the flight from Beijing that basically just managed to land at Heathrow.
Oh, the one that just missed the runway early
And
on.
that was frozen water, the fuel.
That's
They
right.
thought that
BA
the fuel
flight,
had
I
got
remember that.
contaminated in Beijing with water, and the water had frozen in one of the tanks.
That's right, because the
Yes,
flight
that's
path
right.
goes over
Inside
Siberia. It's
the,
very high.
other line,
Yeah,
yeah.
that's right. I remember that.
It's a flight I used to get back from Beijing regularly, that one.
No,
So,
no, they
and
commended the pilot for landing
yeah,
it just
so,
sort of.
you know, any kind of, so we're not in aviation gasoline anymore, we sold our business, but that is, you know, externally, that's something that could be very valuable, how to test for water in aviation.
Right.
Well, that's good to hear. I mean,
How to test water is a small.
do you know what level is it? At the 1% level, 0.1%?
ppm.
ppm. Okay, that's fine. Yeah.
How much time do you have, Kishan? Just to keep
I was hoping to get a train around lunchtime, but I'm
What's that?
flexible.
You're flexible.
Yeah, I could probably. I'm trying to at least one. I'll just
So
check.
we need
About
to,
15 minutes.
yeah. You can leave your bag here if you like, because we'll come back via this way. So you don't have to walk there. It's about 10 minutes walk.
Found out a lot of people were absolutely the last word.
pool or something.